Hello everyone, welcome back with the chapter Circles. Now we are going to discuss about the chapter Circles. So in this video, we are going to discuss about the tangent. In the previous classes, you learnt about some of the properties of a circle. Hence, we shall extend the discussion of the tangent to a circle and study some of the properties of tangents. Okay, so we will consider here a circle with center O and a line AB in the same plane. A circle AB, a circle with center O and a line AB, and a circle here in this figure also same. So then the following figures illustrated the possible relative positions of the circle and the line. So in the first figure, if we see here, the first figure, this is the circle, and AB does not touch or intersect the circle, right? So line AB, in second figure, line AB intersects the circle in two distinct points, and it is called as secant. This line which intersect the circle as two distinct point is known as a secant. Okay, so line AB intersect the circle in two coincident points. Coincident point means that is in exactly one point. Coincident means when both the point coincide each other, means these 2 points coincide at one. So this is exactly one point. It is then said to touch the circle, and this line then come to know as a tangent. Okay, so the word tangent, this tangent comes from the Latin word tangere. This is Tangere. Okay, this is a Latin word. What is the meaning of this word? Which means to touch. This notion of touching is used in geometrical meaning of tangent. So what is the definition of tangent? Tangent. A tangent to a circle is a line that intersects the circle in exactly one point. The point of intersection is called the point of contact or the point of tangency. So this is the tangent. So tangent of a circle is a line that intersects the circle in exactly one point, and that point is known as the point of intersection, or we call that the point of tangency. Now the number of tangent to a circle from a point inside the circle, if we see here is inside the circle. Number of tangent to a circle from a point. This is a point. Suppose this point is inside the circle. So there will be no tangent, zero tangent. On the circle, if we have seen this here, on the circle, this is a circle, and here is on the circle means at the boundary. There is single tangent. And outside the circle, if any point is on outside the circle, if suppose here is this is, so two possible tangents can be drawn. Two possible tangents can be drawn. Right. So inside the circle, if the point is inside the circle, there will be no zero. On the circle means the circle is on the boundary. So there is single tangent, and outside the circle, there will be two tangents. Right. Now we talk about the common tangents. If we see here two circles, and this is one tangent which also going to the other circle, and this is the tangent and going to the other circle. So here if we can see here PT, this is PT or PE, is a common tangent of the two circles PT and PE. These are the two common tangents of two circles. Now we have their categories. So first one is the direct common tangent. If two circles are on the same side of the common tangent, then it is called a direct common tangent. If the two circles, just like PT, if we say PT, both the circles are on the same side of the tangent. So this tangent is known as direct common tangent. If we see here, the two circles are on the opposite sides of a common tangent. If the two circles are on opposite, if we talk about here PE, so one is this side, other is that side. So if the two circles are on the opposite side of common tangent, then it is called the transverse common tangent. So common tangent are of two types. One is a direct common tangent when both the circles are on the same side of the tangent. When opposite side, the transverse common tangent. Okay. Now we have theorems related to the chapter. The tangent at any point of a circle is perpendicular to the radius through the point of contact. The tangent, this is the tangent, this is the radius, is perpendicular to the radius through the point of contact. P is the point of contact. So what is given us? A circle with center O and a tangent AB at point P. What do we want to prove? That OP is perpendicular to AB. Construction: take a point Q other than P on AB, join OQ, let OQ meets the circle at point R. Now, how can we prove this? How can we prove this? Now we can see in the figure that OP is equals to, this is OP is equals to OR. Till here, OP is equals to OR. We can say they are radii of the same circle. Radii of the circle. Okay. Now we talk about here OQ. OQ from figure. What can we write? OR plus RQ. This is OR plus RQ. This was the equation first, and OQ is equals to OR plus RQ. This we can take. So what we can say that OQ is greater than OR, क्योंकि OR में RQ ऐड हो गया तो वो OQ बनता है, तो OQ is greater than OR. We can say this. And OQ is greater than, because OR is equals to OP, so we can write here OP also using 1. Right. So what we can say here, or we can write that OP is less than OQ. It means that OP is less than OQ. So what does it mean? We have a theory here that thus OP is the shorter than any other line segment joining O to any point of AB other than P. So what does it mean? Therefore, OP is the shortest distance. OP is the shortest distance between the point O and the line AB, on the line AB. But we know that the shortest distance between a point and a line is perpendicular distance. So what we can say, OP is perpendicular to AB. This theory we have to write. Thus OP is the shorter than any other line segment joining O to any point of AB other than P. So OP is the shortest distance between the point O, but between the point O and the line AB. But the shortest distance between a point and a line is called the perpendicular distance. So OP is perpendicular to AB. This is our first theorem. Now the converse of this. A line drawn through the end of a radius and perpendicular to it is a tangent to the circle. Now this time what is given to us? A circle with center O, first point OP is the radius. This is the radius, this is given. Second, AB is a line segment, line through P such that OP is perpendicular to AB. This is given to us. What we want to prove? AB is a tangent to the circle at point P. Construction same, take a point Q different from P on line AB and join OQ and it intersect it at point R. Now this time what we can write? Proof what we can take? We can write here that OP, proof we will write OP is perpendicular to AB. This is given to us. So if OP is perpendicular to AB, so we use a converse of that theorem that OP is the shortest distance from O to AB. O to AB. Okay, because perpendicular distance from a point to a line is the shortest distance between them that we have taken. The shortest distance between a point and a line is perpendicular distance. So converse we can take the perpendicular distance from a point to a line is the shortest distance between them. So what we can write? OP is less than OQ. We can write this, OP is less than OQ, or we can write this as OQ is greater than OP. We can write this, OQ is greater than OP. So what does it mean? It means that so Q lies outside the circle. Okay, Q lies outside the circle. So what does it mean? Thus every point on AB other than P lies outside the circle. It means that this shows, we have to write the theory here, this shows that AB meets the circle at point P. AB meets the circle at point P. Q lies outside the circle. So what does it mean? P, every point on AB other than P lies out the circle. This shows that AB meets the circle at point P. So what does it mean? Hence, AB is the tangent to the circle at point P. So this we can say. Most of the time we have to write theory for these theorems because proof is not so particular, but we have to write the theory. So there is a point Q other than P on line AB, join OQ. Here we have to write OP is a perpendicular on AB. OP is the shortest distance from O to AB. Okay, because this we have used. Because we have given here the shortest distance between a point and a line is perpendicular distance. So we can write here the cos. We can write here the perpendicular distance from a point to a line is the shortest distance between them. So OP is less than OQ, or we can say OQ is greater than OP. So OQ is greater than AP. What does it mean that this distance is greater? It means Q lies outside the circle. So what does it mean? That only the P point is on AB. Hence this shows that AB meets the circle at point P. Hence AB is the tangent to the circle at point P. This was a converse of the first theorem. Now we have here the third theorem is there. The length of tangent drawn from an external point to a circle are equal. So what is given to us? This is the figure circle. This is a point outside the circle, and AP and AQ are the two tangent from outside the circle. A circle with center O. A is external point. Two tangent AP and AQ. We have to prove AP is equals to AQ. We have to join here for the construction OP, OQ and OA. This we have to join. Now what is the proof here? the proof we will use, for this we have to take two triangles, or we can say first we will prove here that AP is a tangent. AP is a tangent at P, and OP is a radius. OP is a radius. OP is a radius through P. Okay, so it means that OP is perpendicular to AP. By the first theorem, we will write here the tangent at any point of a circle is the perpendicular to the radius. The tangent at any point of a circle is perpendicular to the radius at the point of contact. Similarly, also OQ is perpendicular to AQ. This we have. Now, in triangle, we will take two triangles, AOP or OPA and triangle OQA. We will take this. What we will write? OP is equals to OQ. Why? Radii of the same circle. Then we will write OA is equals to OA, that is common. Then we will write the above angle. This is angle OPA is equals to angle OQA. Each 90 we have proved above. This is the perpendicular. So triangle OPA congruent triangle OQA by RHS congruency. Then we can say that AP is equals to AQ by CPCT. This is the proof of our theorem. Now we have the next is there, the converse of this. If two tangents are drawn to the circle from external point, then first part, they subtended equal angle at the center. Means this angle will be equal. Or they are equally inclined to the triangles, to the line segment joining the center to the point. These 2 points, these two angles, we have to make them equal. So what is given? A circle with center O and a point A outside the circle, and AP and AQ are the tangents to the circle. We have to prove that AOP is equals to AOQ and angle OAP is equals to angle OAQ. For this, we also have to take two triangles. Then we will take triangles. In triangle, these two triangles we will take. Triangle OPA is equals, and triangle OQA. OPA and OQA, we will take this. So OP is equals to OQ. Same reason, radii of circle. AP is equals to AQ. This we have proved that tangents from an external point are equal. And third is OA is equals to OA. This is common. We are given. So triangle OPA is congruent triangle OQA by SSS congruency. So angle AOP is equal angle AOQ by CPCT, and angle OAP is equals angle OAQ. This is also by CPCT. OAP and OAQ by CPCT, and AOP, AOQ also by CPCT. So these are the 4 theorems. Two are the theorem and 2 are the converse, and the definitions. You can do all these in your notebook. And in the next video, we'll discuss about the exercise. Thank you so much.